Are you serious?
Alright guys, welcome Disney people back. How was your trip? Great? Amazing?
I want to be back because of lunch.
I would love to go. Super
We
jealous.
should all take a trip down, like just the pre-cal class. Go down
Just go. I wish we could. What was your what was the favorite thing that you did or you saw or you experienced?
I rode.
Yeah?
I rode the Expedition Everest 4 times.
Did you?
Yeah, that was funny.
Is that a new ride? I mean, I haven't been to Disney in
I don't-
over 10 years,
I don't
but
think it's new.
uh-huh.
It's newer.
Newer. Okay. I think the last time I went, I was in either 8th grade or 9th grade, something like that.
It goes like backwards or upside down.
A thrill ride. I'd probably like it. Yeah, Rebecca?
Whenever I went to the Animal Kingdom, there was like a balloon set. It's kind of like it's kind of like a four, but like it has 4 tusks.
Mm-hmm.
I thought that was really cool. I got a bunch of pictures with my friend.
Nice. Were you able to touch it? Or
no, it was like in an enclosure, but it was
Okay.
still really cool to see.
Cool. Anybody else? No? Alright. Alright, well, in the meantime, for us that were left in Pennsylvania, we did not move on to, in the unit just because there were so many of you missing. I was not expecting that. I mean, I know in here how many of you were gone, but in some of my other classes there were more gone than I was anticipating. So we did not move forward in the unit. We just did some practice worksheets. So those of us that were here, they got extra practice with logs. But we're going to continue with the unit today. So I know you might feel stressed or overwhelmed coming back because you may have missed a lot in your other classes, but at least you can kind of be self-assured that you didn't really miss anything in here. Okay? But since this is the last section of the unit, we're going to be having a free response day on Wednesday, partner quiz Thursday, review day Friday, and that means unit test next week. So I'm giving you a week's notice. All right? Today we're going to take a look at logarithms and exponentials in their last and final relationship together. We've been noticing how we can use logs to help us solve exponential equations, and we can use exponential equations to help us solve logs. So we're going to analyze that relationship today. And that specific relationship is that logs and exponentials are inverses of each other. They undo each other or cancel each other out. That's why we can use them to help us solve equations. But today we're going to analyze kind of the graphical relationship between these inverse functions, logs and exponentials. We talked about inverse functions in a general sense towards the beginning of the year. And that's what I just want to bring back a little bit first before we go into the logs and exponential parts. So when we were discussing inverses at the beginning of the year, we talked about how we need to first determine if a function is one-to-one in order to even determine if it has an inverse. That's a function. So we're going to go ahead and kind of refresh our memory. Do we remember what it means to be one-to-one? A graph is one-to-one. Want to give it a shot, Tori? Every x only, that's what a function is. Okay, so a function is, you can think about that vertical line test. For every one x, it only has one y. Okay, it passes the vertical line test. Yeah? Is it? Do you know what? I don't have an extra one with me. Is it okay if you just jot down and I'll try to get you a copy tomorrow? Uh-huh. Alright, so to determine if a graph is a function, you can use that vertical line test. For every x, there's one y. What about one-to-one? It's very similar. Instead of a vertical line test, yeah, it's a horizontal line test. So instead of for every x there's one y, this time is for every y there's one x. It kind of switches or flips. Okay, it's that inverse or kind of opposite idea. So for it to be one-to-one, we'll say for every y there is only one x value. Maybe we'll go ahead and write horizontal line test in parentheses. Okay, so vertical line test is to determine if a graph is a function. The horizontal line test is to determine if that function has an inverse. That's also a function. Okay, would also pass the vertical line test. So let's take a look at this exponential function. We did these in the last unit where we have that a, b, c value, okay? And this is graphed to the right. Hopefully we can realize that 2 to the x would be the parent function, and then we are doing a bunch of different things to that parent function. Can we jot those down just as a reminder or a refresher? Can we list some transformations that we notice? Yeah.
X-axis.
All right. Any other transformations? Go ahead, Rebecca. Left 3, up 2. Perfect. So if we were to take the 2 to the x parent graph, flip it over the x-axis, move it left 3, up 2, we would eventually get this graph to the right. So this is kind of the ending graph after the transformations were done. And it looks like they give us some ordered pairs. So the points on the left are the points from the parent function, and then after we were to apply these transformations, maybe use that coordinate rule that we've practiced writing, we would get these coordinates, which we could then plot on the graph. So this is the graph of an exponential function. What if we wanted to find the inverse function of this graph or of these numbers? Do we remember the basic concept of an inverse? How can we get the inverse points? Maybe think about our definition up here of how to determine if a function had an inverse. Instead of using the vertical line test, we used the horizontal line test. We kind of switched the way the line was drawn. Okay, we have this switching going on. What do you think we can do to figure out the ordered pairs on the inverse graph if we were given these ordered pairs on this exponential graph? Want to give it a shot, Maddie? So make this +5 and -1 3/4? Not quite, but I like how you have the idea of switching. Okay, it's not necessarily switching the signs. How else can we maybe switch some numbers in there? Let's see, instead of -5 and 1 3/4, can we write that ordered pair a different way, switching some things? Good, Maddie? We're switching the x's and y's. So we're not changing the signs, okay? The numbers stay the same, it's just that we're switching the x coordinate and the y coordinate. So we'll go ahead and switch the x and y numbers. You can write coordinates, I just ran out of room there. Alright, so let's go ahead and we'll actually do that in the table at the bottom. So these were the points on the f of x graph, okay, that exponential graph that we started with. Let's go ahead and see what the points would look like on the inverse graph, that little power of -1. Okay, we talked about or saw that notation towards the beginning of the year when we were introducing inverses. So Maddie said we can simply just switch the x and y coordinates. So our new x coordinate would be 1 3/4, and the new y coordinate would be -5. Let's go through all the other ordered pairs and we'll find their inverse points. Now that we have the inverse points, let's go ahead and plot them, and that can produce for us the inverse graph. Alright, now before we connect the dots, there's one other characteristic that we got to make sure that we label here. Because if you take a look at the exponential graph, we not only flipped the ordered pairs to get our new inverse ordered pairs, but the exponential graph also had a horizontal asymptote. Okay, that's a graphical characteristic. It's a part of the graph. So if the f of x graph has a asymptote of some type, the inverse should also have an asymptote of some type. What do you think?
Would it be 0 since it's over log x0?
Where would you want to draw it on this one? You said 0?
So on the x-axis.
Like this? Well, you can't necessarily draw it on the x-axis because notice how we have a point on the x-axis. Remember, an asymptote you approach but you don't touch. So you have the right idea. We should have one somewhere, okay? But let's think about this. This was a horizontal asymptote, yeah? It should be a vertical, right? If we switch the x's and y's, instead of having a horizontal asymptote, this one would have an equation of y equals 2, because it's a horizontal flat line at a y value of 2. If we were to switch that y variable with an x, notice how this asymptote should be at the x value of 2. So on your graph, you would have to draw in a vertical dotted line. And if we were to draw it in, notice how the points kind of approach that dotted line, but they're never ever going to touch it. You see how those three are pretty close right there? So now that we have that other or final characteristic in, maybe we can go ahead and draw the inverse graph. So that's something pretty important to note there. So we'll say the horizontal asymptote on the exponential graph becomes a vertical asymptote on the log graph. Okay, we just graphed a logarithmic function because logs are inverses of exponentials. So notice how logarithmic graphs kind of have that exponential shape, okay, that kind of grows really quickly or decays, but in this time we have a vertical asymptote instead of that horizontal one. Okay, so logarithmic graphs look very similar to exponentials because they're inverses. They have that relationship between them. Okay, so what we're just going to explore today is this idea of the inverse relationship between exponentials and logs a little bit further. Let's not forget, though, that the whole idea of an inverse is to switch the x and y variables or coordinates. It kind of all comes back to that idea. All right, so let's go ahead and try to find the equation of that inverse. We found the graph of the inverse. Let's see if we can try to figure out the equation of that logarithmic graph. So if we can try to think about a process, because I know, again, some of us are pretty procedural, maybe we can write down some steps that we could try to do. The whole idea of an inverse is to switch the x and y variables or coordinates. So that might not be a bad idea to start with. The problem is when we switch the x and y variables, it's now an x equals equation, and you're always used to a y equals equation all the way back from Algebra 1. So to make it look a little bit more appealing to us, instead of an x equals equation, we're going to go ahead and try to solve for y. That way it looks a little bit more familiar. Are these kind of ringing a bell? back to us a little bit for the beginning of the year. Okay, so we're going to switch the variables, we're going to solve for y, but since this inverse equation is really special, okay, we're going to replace the y variable with that inverse notation, that f to the negative first power. That's just telling you and whoever looks at your paper, maybe a friend if you're going to talk about or go over some work, that they know that that equation is an inverse. All right, so we're going to go ahead and take this exponential equation from the front. We identified the transformations from it. Let's see if we can find the inverse function. Now, since the original equation is an exponential, we should be anticipating some type of log in this inverse, because after all, exponentials and logs are inverses of each other. So let's go ahead and switch the variables. We'll have x equals -2 to the y plus 3 power. Technically, that's an inverse because we switched the x's and y's, but it just doesn't look nice to us because of that x equals. We're used to y equals. So our goal is to try to get that y variable all by itself. And this is where we're going to have to do a little bit of solving, like in the last section that we covered, or the practice that those of you that were still here last week got. So let's see, how might you want to start to solve for y? Can we move some numbers to the other side? Let's go ahead and subtract the 2. I think that was an easy first thing to do. Is there something else that's kind of easy that we could probably move over next? Do we see that negative out front? Maybe we can move that over, get rid of that negative. So that would switch all the signs on the other side. All right. Now the y variable is in the exponent spot. We can't really do anything with that yet, or the 3, because that's in the exponent spot as well. We need to somehow move over this base of 2. So if we're going to move an exponential base, we're going to have to convert it to a log. The question is, what would this equation look like if we were to convert it? Let's see, we'll start with baby steps. So I'll write the word log. I got to figure out what's that little base of the log, what's the argument of the log, and what does the log equal. We got to fill in those 3 different spots. You want to give it a shot, Tori? Okay. There we go. Logs are powers, so that's what the log should equal, that power of y plus 3. The base of the exponential was 2, so that should be the base of your log. And then that leaves the argument to be the other side of the equation, that negative x plus 2. So we converted it. That's nice because now we can easily solve for y. Notice how we can just subtract that 3 over. So log base 2, negative x plus 2 is the argument, and then subtract 3 on the other side. Alright, so we got the y variable all by itself. This is our inverse equation. This is actually the equation of that log graph we drew on the other page at the very bottom. Now the last thing we got to do, instead of having the y there, we'll just go ahead and replace it with f inverse, because this equation is the inverse of the f exponential we started with. So it's a little f to the negative 1 power. Okay, so switch the variables. I think we can do that. Solving for y might get a little tricky, but we got to utilize the logs to help us with that. And I think we can write f to the negative first instead of a y. Okay, we're going to try some more just to get this to kind of sink in a little bit. All right, so let's try another one. For each of the following, we're going to find the inverse equation. So this first one actually looks very similar to the one we just did. Slightly different, but let's go ahead and switch the variables. And we're going to try to get that y all by itself. What do you want to move over first? Yeah. Yep, let's go ahead and add the 3 over. Where do you want to go next? You want to keep going? Yeah. We're going to make it a log. All right, so we're going to move the 2 to the other side. We're going to go ahead and convert it to a log. The 2 is the base of the exponential, so that would be the base of the log. Logs are powers, so this log should equal that negative y plus 3 power, which means the argument should be that x plus 3 that was on the other side. Okay, we converted that exponential to a log. We still got to get y all by itself, so maybe we can subtract the 3 over. And then last but not least, we can divide that negative. So everything's just going to switch a sign. All right, so now that we got the y all by itself, we can just replace it with it to an f to the negative first power. All right, let's try another one. We're going to switch the variables and try to get y all by itself. What do you want to move over first? Yeah. Okay, let's move over the 3. I like it. Then what? You want to keep going? Yeah? It's going to be a natural log, right? So we're going to move the base of e to the other side. We'll convert it to a log. It would have to be natural because it was a base of e. So we'll be left with y plus 2. And then solving for y, we can just subtract the 2. And instead of y, we'll write f inverse, or f to the negative first. We doing okay? Do you guys think you can try the last one? Bless you. How'd you do? I'm seeing head nods. That's good. Do we want to go over any part of that? We're okay? Perfect. All right. So what I want to try to do is bring all of this kind of inverse relationship together, and we're going to fill out a nice kind of go-to chart on the next page. Remember when we were doing exponential functions, and I would just give you an equation and ask you, where's the horizontal asymptote? Is it above or below? What's the domain and the range? You could identify all that information just off of an equation. Alright, so in the last unit, we got really good with using exponential equations to identify different graphical characteristics. My goal is for us to get just as good with these logs. Now, it's not going to be that difficult for us because if logs are inverses of exponentials, and we're already so good with exponentials, these logs could be fairly easy for us to kind of grasp. So we're going to explore again that graphical connection between exponentials and these logarithms. So these are the three equations that we just did on the other page that we found the inverse equations for. We're going to go ahead and just look at these exponential ones first to determine the domain and range and where that horizontal asymptote is. And from there, we're going to answer a bunch of different questions about the inverse because of this relationship between exponentials and logs. So, can we determine the domain, the range, and where the horizontal asymptote was for this first exponential equation? We gotta kind of go back to the last unit. Let's maybe start with the horizontal asymptote. Can you determine where that is? Yeah. Oh, there we go. Y equals -3. Okay. What about the domain of an exponential? Go, Rebecca. Always. Good. What's trickier is the range, because you got to determine, first of all, we know where the horizontal asymptote is, but we got to determine, are we above that, going up towards positive infinity, or are we below that, going towards negative infinity? How can we identify if we're above or below that horizontal asymptote? Yeah. The A value, which is? That's the base. If I were to put a parentheses around there, what would be the number out front? It would just be 1, okay, which is positive. So are we above or below that asymptote? Above, okay. So the range, this horizontal asymptote is the lowest value, so that would be the first number written. And then if we're above that asymptote, we're going to go up towards infinity. So that'll be our highest value. All right, so to help you with the range, you got to determine, are you above or below? Okay, what's that A value? Let's see, can we take this information from the exponential and figure out the domain, the range, and the asymptote for the inverse, aka the log? Okay, domain, range, and then logs have vertical asymptotes. We want to try to decipher any of those three? What do you think, Rebecca? This time, right, this time it would be an x equals -3 because we switched those variables. Good. What about the domain and the range? Good, Maddie? Uh-huh. And what about the domain? Want to give it a shot, Rebecca? There we go. All right. Inverses, there's a bunch of switching going on. Doesn't the domain necessarily or technically mean x values because we trace the graph left to right? And if we're switching those x values, they should become y values, aka a range in the inverse. So we have a whole bunch of switching going on. If you can determine the domain and range of the exponential, you also know the domain and range of the log, that inverse. They just switch. All right. Let's check out maybe the equation of the inverse function. We did this on the other page. You might have to flip, perhaps, to reference. But after we switched the variables and solved for y, I think we got negative log base 2 of x plus 3, and then a plus 3 on the end. Okay, we did that on the other page. All right, let's check out these last two columns. They want us to set the argument of the inverse, meaning this log, equal to 0 and solve for x. So the argument is that x plus 3 portion. And if we solve for x, looks like we get negative 3. The last column's really similar, just instead of taking the argument and setting it equal to 0, we want to set it greater than 0. Why do you think we're setting the argument greater than 0? What's special about the argument of a log? Say it. It can't be negative and it can't be 0, right? So this argument, this x plus 3, must be positive, meaning greater than 0. That's what we're checking out here. Essentially, what x values are we able to plug in here that would not make it negative or 0? So solving for x, we'll get x is greater than negative 3. Can we think about what these two items from the last two columns are representing in terms of this log equation? Maybe take a look at the domain and range that we found as a little hint. What does this x value of negative 3 represent? And what do all of these x values greater than negative 3 represent? Do you see it, Rebecca?
So that the first x value
Uh-huh.
represents the vertical asymptote,
Uh-huh.
and the second column just is the domain.
Is the domain. Yep. Notice how x is greater than negative 3. We said the domain was negative 3 up to infinity. Any number you want greater than negative 3. So these last two columns are representing ways for us to figure out where is the vertical asymptote on the logarithmic graph and what is the domain of that logarithmic graph. Meaning, are we to the right of the asymptote or to the left of the asymptote? A little different than exponentials, because exponentials we were either above or below. Now that we're switching it, the graph is either to the left or to the right of the vertical asymptote. Okay, we're going to see if that connection kind of follows through with all these other examples. Let's try the next one. Domain, range, and horizontal asymptote because it's an exponential. Want to give it a shot? Yeah.
For the domain, it would be negative 3 to positive infinity.
Always, yep.
And then for the range, it would be 3 to infinity.
How'd you know?
So since before the natural log, it would be a 1, so it would be above the horizontal asymptote.
Okay.
So it would go to infinity. And then the horizontal asymptote would be 3.
Would be 3, right. This time the horizontal asymptote was just in front of the exponential. If you wanted to rearrange this and put the plus 3 on the end, that means the exact same thing. Okay, don't get tripped up that they just put it in a different spot. And then Emily also said that in front of the e, I think she said exponential by, or natural log by accident, in front of the e there's a 1, a positive number. So we should be above that horizontal asymptote, meaning we're going towards infinity. So if these are the graphical characteristics of the exponential, let's see if we can identify those same graphical characteristics for the log, aka the inverse. Yeah.
Domain would be 3 to infinity.
Uh-huh.
And then the range would be negative infinity to positive infinity.
Always,
and
yep.
then the vertical asymptote would be x equals negative 3.
A positive 3.
Positive 3.
That's okay. Good. All right. Let's go ahead and write the equation we found from the previous page. That was the natural log of x minus 3 minus 2. All right, so let's set the argument equal to 0. We got x equals 3. Is that the same vertical asymptote? we identified previously? Good. I'd be willing to bet my last dollar that someone is going to look at this natural log equation and tell me the vertical asymptote's at -2. Do you see why someone might make that mistake? We're used to going towards that last number, but that's only for exponentials. Okay, for logs, the asymptote actually comes from the argument. A little tricky. Let's check out the domain piece. So we're going to take that argument again, and this time set it to greater than 0, because it can only be positive. We know we can't have a negative or a 0 in that argument spot. So we have x is greater than 3. Doesn't that match the domain we identified? Any x value you want to plug in greater than 3. How are we doing so far? We're doing okay? All right. We'll save the last one for tomorrow as a refresher, okay?